Imagine waking up, grabbing your phone off the nightstand, and just checking the weather report for the day.
Right. Something we all do, like completely mindlessly.
Exactly. And then, while you're drinking your coffee, you open a browser and you order I don't know, a midnight blue reinforced smartphone case. SKU 88472. It all feels so effortless. But, I mean, consider what just happened beneath the glass of that screen. What actually makes that simple routine possible?
Because your weather app isn't just, guessing. It's actively pulling localized data from these massive global systems that are tracking atmospheric pressure, temperatures, radar, all worldwide in real time.
Yeah, and the search engine you use to find the phone case, it literally just indexed millions of websites in a fraction of a millisecond. And the online store where you clicked buy, well, it simultaneously managed your customer account, checked real-time inventory levels across multiple warehouses, securely routed your payment, and triggered a shipping cascade.
It's wild when you actually stop to think about it. The underlying reality is that, whether you realize it or not, you are interacting with databases from the exact moment you wake up until you set down your last digital device at night.
It is entirely invisible to us by design, but it forms the absolute foundation of modern business. I mean, the sheer volume of instantly retrievable information required just to get you a weather forecast and route a piece of plastic to your doorstep is staggering.
Data really is the lifeblood of the global economy. Without it, everything just stops.
Well, welcome to the deep dive. Today, we are immersing ourselves in Module 2, Databases. This is based on the Text Connect Master, Management Information Systems by Richard Tedmon and Casey Wilhelm, the 2026 edition from McGraw-Hill.
Yes, and this deep dive is produced specifically for the undergraduate business majors and the professionals over at the Dr. Sampak College of Business at Tarleton State University.
We are going to trace the hidden life cycle of that smartphone case order, really dig into it, to understand exactly how organizations structure, store, and leverage massive amounts of data to maintain a competitive edge.
But, before we break down the architecture of databases, we need to bridge this back to where we came from. Like in Module 1, Investigating MIS, we explored the evolution of management theory.
Right. We looked at historical thinkers like John Locke with his labor theory of property and Adam Smith, the father of economics who championed the division of labor.
Exactly. We saw how those foundational ideas of organizing human effort eventually merged with modern technology, moving from the Industrial Revolution into the digital age, looking at systems like mobile point-of-sale stations, massive enterprise resource planning systems, ERPs, and the whole advent of cloud computing.
And the critical connection to today's discussion is that all those incredible systems from Module 1, like the ERPs and the global point-of-sale networks, they're essentially just empty architectural shells.
They're like beautiful, incredibly expensive engines sitting in a factory, but they are completely inert without fuel.
Yeah, the information is that fuel. So today's deep dive is looking at the internal mechanics of the fuel tanks and injection systems that power those applications, which are the databases.
Because a management system is strictly bound by the quality and organization of the data it holds. If the underlying data architecture is flawed, the most expensive ERP system in the world will literally still grind a business to an absolute halt.
Before we start mapping out how these data architectures are built, I want to quickly invite you, the listener, to like, subscribe, follow, and share this deep dive.
Yeah, leave a comment down below to stay updated with your coursework and join the ongoing conversation. Hearing how you apply these concepts in your own careers really drives this community forward.
Okay, let's unpack this. Let's start by looking at the fundamental problem businesses faced before modern database management systems even existed.
Right. For decades, organizations had to rely on traditional manual file systems. Physical paper, manila folders, filing cabinets.
Sounds like a nightmare.
It was. And as computers entered the workspace, this evolved into simple, standalone digital files. Think of like a basic spreadsheet saved on a single employee's local hard drive.
But today, organizations use database management systems, or DBMS, which is a highly complex software program, usually created by major vendors like Oracle, Microsoft, or IBM, used to create, process, administer, and secure a database.
Exactly.
But I want to challenge the necessity of that complexity for a second. To a casual observer, it might sound like we just swapped physical paper files for digital files in a folder. If I own a small business, why can't I just keep all my customer data in a series of digital spreadsheets? What actually fails when a business scales using just flat files?
The structural failure comes down to two cascading pitfalls, basically: data redundancy and data inconsistency. Let's look at a concrete business scenario from the Tedmon and Wilhelm text to make sense of this. Imagine managing the operations for a large local gym.
Okay, I'm with you.
You have a highly active customer who is enrolled in a Tuesday yoga class, a Thursday spin class, and a Saturday weightlifting clinic. In a traditional flat file system, the instructor for each class maintains their own separate digital roster.
So the yoga instructor has a spreadsheet, the spin instructor has one, and the weightlifting coach has one.
Correct. That customer's details, their full name, phone number, emergency contact, home address, are typed out and stored in the yoga file, typed again in the spin file, and typed a third time in the weightlifting file.
Oh, wow.
That is data redundancy. You are storing the exact same data multiple times across the organization, which wastes storage space, sure, but more importantly, it sets a massive trap for the business.
Because the moment that customer's life changes, the trap springs. Like, let's say the customer moves to a new apartment across town. They walk up to the gym's front desk and say, I have a new address and a new phone number. The employee at the desk updates the master billing file, and maybe they remember to update the yoga class file. But they have no idea this person also takes spin and weightlifting, so those files just remain untouched.
And the operational consequence of that is data inconsistency. The gym's internal records now literally contradict each other. The billing department has one address, but the spin class roster has another.
So if the gym attempts to mail a critical billing statement or an exclusive promotional offer, the system cannot definitively answer which address is the actual truth.
Exactly. The business logic starts to fail. The gym wastes money on returned postage, the customer misses a critical communication, and their overall experience is degraded. A DBMS solves this through structural data centralization.
Okay, so instead of separate files, the DBMS creates a single central repository.
Yes. The yoga roster, the spin roster, and the billing department don't store the customer's address anymore. They simply point to the one centralized record in the DBMS.
Which ensures what we call data integrity, meaning the data in your system is reliable, accurate, and perfectly aligned with the organizational goals. When the customer updates their address, you change it in exactly one place.
And instantly, every single application or department that relies on that data pulls the correct, updated address.
So the DBMS essentially acts as a single source of truth. Let's transition from the why to the how, though. If we open up this DBMS engine, what does the internal architecture actually look like? Like, if I'm an undergraduate business major, I need to know how my company's data is structured.
Well, the overwhelming standard for decades has been the relational database. A relational database organizes data into highly structured two-dimensional grids called tables.
Okay, tables.
Yeah, and each table holds a specific category of objects. You will have one table strictly for customers, another completely separate table for inventory, and another for orders.
Got it.
Inside these tables, the horizontal rows are called records, and the vertical columns are called fields.
To tie this back to our smartphone case narrative from earlier, if I am looking at the online store's customers table, a single record one horizontal row represents all the information for me, the specific buyer.
Right.
And the fields, the vertical columns, would be the specific attributes of my identity. First name, last name, email address, shipping address.
And this is where the business professional really needs to understand the underlying logic. Because a massive e-commerce company doesn't operate on just one table. They operate on thousands of interconnected tables.
Right, obviously.
To link them together, without creating the redundancy we just talked about, relational databases rely on an ingenious mechanism using primary keys and foreign keys.
A key acts as the connective tissue between these isolated tables. Let's break down the mechanics of a primary key first.
So a primary key is a specific field, a column within a table that contains a completely unique identifier for every single record. It guarantees that no two rows can ever be confused.
Oh, like in a university setting, the primary key in the student's table would be your student ID number.
Exactly. You might share a first and last name with another student, but your ID is mathematically unique within that system.
That makes perfect sense for isolating a specific record. But how does that actually help us connect tables together? If I place an order for that midnight blue phone case, the business needs to connect my customer record to the inventory record.
They do that using a foreign key.
Yeah.
Let's say the store has an orders table. When you hit buy, the system generates a new row in the orders table, but it does not copy your name, your shipping address, or your email into that order record.
Because that would be data redundancy again.
Exactly. Instead, it simply includes a column for customer ID, and it drops your unique primary key into that slot. In the context of the orders table, your customer ID is now acting as a foreign key.
So it functions like a digital signpost. The order record says, I'm in order for SexAU 88472. If you want to know who is buying it and where to ship it, take this customer ID, go over to the customers table, and look up the details.
Yes. And what's fascinating here is that the brilliance of this design is that it enforces referential integrity.
Referential integrity, what does that mean exactly?
It's a set of rigid rules programmed into the DBMS that ensures the relationships between your tables remain logically sound and consistent.
Okay.
Let's look at the mechanical safeguard this provides using the textbook's example. Imagine your customer ID in the primary table is 1556. You have placed dozens of orders over the years, meaning the orders table has dozens of rows where the foreign key is 1556.
Okay, so my customer ID is heavily embedded in the historical sales data.
Now, suppose an inexperienced employee goes into the customer's table and attempts to delete record 1556 entirely. If the software allowed that deletion to execute, you would instantly have a massive logical breakdown.
Oh, because the orders table would still contain all those historical purchase records pointing to customer 1556, but customer 1556 no longer exists in the primary table.
Precisely. You would create a cascading error. The accounting department would try to run a revenue report. The system would try to look up who made those purchases, find an empty void, and likely crash or generate a corrupted report.
In database architecture, that is called an orphaned record, right?
Yes, an orphaned record. Referential integrity rules physically block this from happening. A properly configured DBMS will just abort the deletion command.
It'll just say no.
Exactly. It returns an error stating that you cannot delete the primary key because there are dependent foreign keys in the orders table. You would first have to handle the associated order records, maybe by archiving them, before the system allows you to remove the master customer file.
It essentially prevents human error from destroying the mathematical logic of the business. And to manage all of these rules, like knowing which columns are primary keys, what type of data is allowed in a field, the database relies on something called metadata.
Metadata is frequently defined simply as data about data. It is stored in a hidden architectural file called a data dictionary.
A data dictionary.
Yes, and the data dictionary dictates the parameters of the system. For instance, it tells the database that the phone number field in the customer's table is strictly limited to 10 numeric digits.
So if a user tries to type the letter A into that field,
The data dictionary flags the violation and the DBMS rejects the input. Usually, only database administrators interact directly with the data dictionary, but it is the foundational rulebook that prevents the system from ingesting garbage data.
which brings us to the design phase. I mean, if I am an operations manager and my team needs a new database to track logistics, I can't just start randomly creating tables and assigning keys. I need an architectural blueprint before a single line of code is written.
Absolutely. Attempting to build a database without a rigorous blueprint is akin to constructing a skyscraper without architectural schematics. I mean, the structure will inevitably collapse under its own weight. In the context of databases, that blueprint is called an entity relationship diagram, or an ERD.
Let's dissect the components of an ERD. We are mapping out three main elements: entities, relationships, and attributes.
Entities represent the distinct objects, concepts, or events that the business needs to track. Grammatically, they are almost always nouns: a customer, a product, a supplier, an employee. On the diagram, these are usually represented as large boxes.
Okay, and the attributes, what are those?
Attributes are the specific data points or characteristics associated with each entity. They translate into the fields and columns of your future tables. For the product entity, the attributes would be the CU number, the manufacturing cost, the retail price, and the weight.
So we have boxes representing the nouns and lists inside them representing the adjectives, basically. The crucial part of the blueprint must be the relationships, then the verbs that connect these boxes together.
The relationships map out the business processes. An employee manages a store. A customer places an order. A supplier delivers parts.
Right.
When building an ERD, database architects must define the cardinality of these relationships, which dictates how many instances of one entity can associate with instances of another. There are three primary types to understand.
Let's walk the listener through those with concrete business examples, starting with the one-to-one relationship.
A one-to-one relationship dictates that a single instance of an entity is associated with exactly one instance of a second entity, and vice versa.
Okay.
A classic example is a corporate vehicle fleet. You have an entity called company car and an entity called executive. A specific company car is assigned to one and only one executive, and that executive is assigned one and only one company car.
That's very clean, very straightforward. What about the one-to-many relationship? I imagine this is like the most common in business.
It is ubiquitous. A one-to-many relationship means a single instance of the first entity can be associated with multiple instances of the second entity, but an instance of the second entity can only associate with one instance of the first.
Right.
Consider a university framework. A professor and their students in a specific lecture. One professor teaches many students. However, from the perspective of that specific lecture, a student has only one professor.
Or, going back to our e-commerce example, one customer can have many orders, but a specific order can only belong to one customer. The relationship branches out in one direction. That leaves the most complex structure, the many-to-many relationship.
A many-to-many relationship occurs when multiple instances of one entity can associate with multiple instances of another. Returning to the university setting, look at the entities student and course. A single student enrolls in many different courses. Simultaneously, a single course contains many different students.
The web of connections becomes incredibly dense there. So you sit down with the stakeholders, draw out the ERD on a whiteboard, identify all the entities, list the attributes, and define the cardinality. You have your blueprint.
Yes.
But a blueprint can be poorly designed. How do database architects ensure the structure is actually optimized for a live business environment?
They subject the design to a rigorous mathematical process called normalization. Normalization is the systematic method of evaluating your tables and breaking them down into smaller, highly specialized tables to eliminate data redundancy and prevent insertion, update, or deletion anomalies.
Let's dig into the actual mechanics of why normalization is necessary, because it goes beyond just saving hard drive space, right? I mean, storage is cheap.
The storage space is almost secondary today, given how cheap disk space is. Normalization is entirely about transaction integrity. Let's trace our smartphone case order.
Okay.
If the database was not normalized, the system might have a single massive table called sales. When you buy the phone case, it records your name, your address, the phone case SKU, the phone case color, and the manufacturer's details all in one row.
And if the manufacturer changes their company name from, say, Casico to Global Cases, Inc., the business has a massive problem.
Exactly, because Casico is written into millions of individual sales records, the database must execute an update command that searches and rewrites millions of rows. This consumes massive amounts of CPU cycles, locks up the database table so new orders can't be processed, and risks data corruption if the system crashes halfway through the update.
Normalization solves this by isolating the data. You break it down so that the manufacturer's details live in their own dedicated suppliers table. The sales table just uses a foreign key to point to the supplier.
Right.
If the supplier changes their name, you update exactly one row in the supplier's table. The CPU executes the change in a microsecond, no tables are locked, and transaction integrity is preserved.
Normalization ensures that every piece of data depends on the primary key, the whole primary key, and nothing but the primary key. It creates a robust, bulletproof environment for processing live, high-volume transactions, which we call OLTP, online transaction processing.
Let me challenge that premise, though.
Yeah.
If I normalize my database to the extreme, I might break my data up into 50 different tiny specialized tables.
Yes.
If the CEO suddenly asks for a comprehensive end-of-year sales report that requires data from the customer, the product, the supplier, the shipping logistics, and the marketing campaign, the database has to piece all 50 of those tables back together to generate the report.
And that exposes the fundamental trade-off in database architecture. Reassembling normalized data requires the CPU to execute complex JSON operations.
Right.
The processor has to read from the customer table, hold it in memory, search the orders table for matching foreign keys, load that into memory, and so on. Running a massive analytical query on a highly normalized database will result in severe disk latency. The report might take hours to generate, and the computational strain might literally slow down the live cache registers.
Which brings us to the opposing architectural strategy, denormalization. Why would a business intentionally undo all that careful normalized organization?
Because different tasks require different architectures. Denormalization intentionally introduces redundancy by combining data from multiple tables back into a single wide flat table. You do this to drastically reduce read latency.
So the CPU doesn't have to perform any complex joins, it just reads straight across the wide row like reading a book.
Precisely. Denormalization is the standard strategy for data warehousing. A data warehouse isn't processing live, minute-by-minute customer transactions. It is a massive, read-only repository of historical data used strictly for analysis.
Oh, I see.
In an analytical environment, reading speed is prioritized over updating efficiency. You accept a storage redundancy because it allows the CEO's massive year-end report to generate in seconds rather than hours.
So normalization is for the live cash register. Denormalization is for the historical analysis in the back office. That structural distinction is a crucial takeaway for our listeners. Now, assuming we have our tables perfectly designed, how do we actually interface with this machine? We can't just speak conversational English and say, hey server, how many midnight blue phone cases did we sell last Tuesday?
You cannot use conversational English, no. But you use a standardized language designed to be remarkably close to it. SQL, or Structured Query Language. SQL is a domain-specific language used universally to manage relational data, generate queries, update records, and build reports.
Let's talk about SQL's longevity. It was developed in the 1970s. I mean, in the tech world, a 50-year-old language is practically a fossil. Most programming languages from that era are completely obsolete. Why are we still teaching business majors SQL in 2026? Why hasn't it been replaced by something newer?
SQL has survived because it is a declarative language as opposed to an imperative language.
What's the difference?
In an imperative programming language like C++ or Java, you have to write out the exact step-by-step logic of how the computer should execute a task. You have to tell it how to allocate memory, how to loop through arrays, how to read the physical disk.
You have to micromanage the machine.
Yes, but SQL is declarative. You simply declare what you want the final result to be, and the database engine's internal optimizer figures out the most efficient how.
Oh, that's brilliant.
You tell SQL, I want the total sales of blue cases. The DBMS engine decides whether to use an index, how to allocate RAM, and how to scan the disk. This decoupling of business logic from underlying machine logic means that as hardware evolved from mainframes to cloud servers over the last 50 years, the SQL language itself didn't actually need to change.
That is a profound architectural advantage. You don't have to rewrite your entire corporate query library just because you upgraded your servers. Let's look at the basic syntax components of SQL just to give a feel for it.
SQL syntax is built on a few core components. Statements are the broad commands that tell the database what action to take, like select, insert, update, or delete.
Right.
Queries are the specific requests to retrieve data based on criteria. Expressions calculate and produce specific data values. And clauses or predicates are the filters, the rules that limit the data returned, like specifying a date range or a specific geographic region.
Let's ground this in a real business scenario from the text. Imagine I'm an HR manager at a warehouse logistics center. I need to add a newly hired employee into our database. The employee's last name is Lehman, first name is Pat, they are assigned to the loading dock, and their starting hourly rate is $22. Walk me through how this SQL statement is actually constructed.
The construction is strictly logical. You begin with the action statement and the target table. You type, insert into employees. The system now knows it is preparing to write data to the employees table.
Next, I need to tell it which specific columns I have data for.
Correct. In parentheses, you define the fields. You type, parenthesis, last name, first name, work area, hour rate, close parenthesis.
The order here must be critical.
It is the defining map. Because the next step is providing the actual data, and the data must sequentially map to those fields. Use the clause values, followed by the data in parentheses, encapsulated in single quotes. So you type values, parentheses, quote Lehman, end quote, quote Pat, end quote, loading dock, end quote, 22, end quote, close parenthesis.
Putting it all together, that's insert into employees parenthesis, last name, first name, work area, hour rate, close parenthesis, values, parenthesis, Lehman, Pat, loading dock, 22, close parenthesis. While it's highly structured, a manager doesn't need a computer science degree to understand the intent of that code.
Exactly, which empowers business analysts and managers to directly interface with the data without constantly relying on IT developers to write basic reports.
But the textbook outlines a massive pivot happening in the industry right now. As resilient and powerful as relational databases and SQL are, they are facing a severe challenge from the modern web. We are seeing a massive rise in NoSQL databases. What does NoSQL stand for, and why the sudden shift away from tables?
NoSQL generally stands for not only SQL or simply non-relational. The shift isn't because relational tables are bad, it is because they are structurally insufficient for modern web data. Relational databases require a rigid, predefined schema. You must know exactly what columns you need before you enter data.
Which worked perfectly for 1990s accounting software where everything was a neat text field or a number.
But consider the data a business collects today. It is unstructured or semi-structured data. It is erratic social media feeds, massive video files, audio recordings, IoT sensor logs that change format depending on the device, and complex, layered web app interactions.
Yeah, that doesn't fit in a table.
No. If you try to force unstructured data into a rigid relational table, the system breaks. Furthermore, relational databases scale vertically, meaning to handle more traffic, you have to buy a bigger, more expensive centralized server.
And there is a physical limit to how big one server can get.
Precisely. NoSQL databases solve this by abandoning the rigid table structure and enabling horizontal scaling, meaning you just distribute the data across thousands of cheap commodity servers in the cloud. There are 4 primary architectures of NoSQL databases you need to recognize: key value stores, document databases, column-oriented databases, and graph databases.
Let's focus our deep dive on the document database, because the Tedmon and Wilhelm text uses a brilliant clothing store example that really clarifies the difference. If I have a highly normalized relational database for an e-commerce clothing store, the data for a single product, let's say a pair of boots, is shattered across multiple tables.
Right.
One table holds the boot's base SKU, another table tracks available sizes, a third table tracks the available colors, and a fourth links it to the footwear department.
And to display that single pair of boots on a website, the relational database's CPU has to execute complex join operations across all those tables in real time.
But in a NoSQL document database, we change the architecture entirely. Instead of shattering the data, all the information is packaged into one self-contained, flexible document, usually written in a format called JSON.
The physical representation of that document on the server looks fundamentally different. It is a single hierarchical text block. The document lists an ID of 15. Below that, the item is defined as boots. The department is shoes. Then, instead of pointing to a separate table for colors, it simply includes an array within the document: colors, bracket black, brown, close bracket. It includes another array: sizes, bracket S, M, L, close bracket.
Everything the web browser needs to render that product page is sitting in one contiguous block of memory.
The computational overhead drops dramatically. When millions of customers click on products during a Black Friday sale, the NoSQL database doesn't perform millions of join operations. It simply grabs the single requested document and serves it up instantly. This allows for unparalleled retrieval speed and rapid horizontal scalability.
The scale is almost incomprehensible. The text notes that Amazon's DynamoDB, a proprietary NoSQL database, handles over 20 million requests per second for heavy-hitting companies like Lyft and Airbnb. The relational model simply cannot process 20 million join operations a second across distributed global servers without massive latency.
It is literally the architectural backbone of the modern high-traffic internet.
Here's where it gets really interesting, because there is no such thing as a free lunch in systems architecture. What is the fundamental trade-off of NoSQL compared to our trusty SQL relational databases? If we gain infinite speed, what do we actually lose?
We lose built-in consistency and data security. Relational databases operate on strict ACID compliance, atomicity, consistency, isolation, durability. This ensures that a transaction is processed with absolute mathematical certainty.
Right.
If a bank transfers money, the system guarantees the money leaves account A and arrives in account B simultaneously, or the transaction fails completely. NoSQL often operates on base principles, basically available, soft state, eventual consistency.
Eventual consistency sounds terrifying for a bank.
It is. In a distributed NoSQL system, if a user updates their profile on a server in New York, a user querying a server in Tokyo might see the old data for a few milliseconds before the servers sync up. It is eventually consistent. Furthermore, because NoSQL lacks the rigid, predefined schemas and strict relational constraints, they inherently lack many of the native security and data integrity firewalls that relational databases have perfected. Businesses using NoSQL must manually code robust security and validation layers at the application level because the database won't catch the errors for them.
So you trade structural safety for blinding speed and massive scale. And speaking of massive scale, this transition perfectly illustrates the concept of big data. I mean, big data is perhaps the most overused buzzword in corporate meetings, often used just to describe a really large Excel spreadsheet. But in MIS, big data has a strict structural definition.
It does. Big data refers to datasets with volumes so massive and architecture so complex that traditional data processing software, like a standard relational DBMS on a single server, simply cannot capture, store, manage, or analyze the data within a tolerable time frame. In our field, we define big data using the 4 V's: volume, variety, velocity, and veracity.
We need to thoroughly unpack each of these, starting with volume. We aren't talking about gigabytes.
Volume is the sheer raw scale of the generated data. The text notes that most large enterprise companies today are managing over 120 terabytes of stored data. To put that in perspective, a single terabyte is roughly equivalent to 250,000 high-resolution photos. 120 terabytes is an ocean of information, and companies are adding to it exponentially every single day.
The storage infrastructure required just to house that is staggering. The second V is variety, which ties back into our NoSQL discussion.
Variety refers to the structural diversity of the data. Historically, a business's data variety was low. It was almost entirely structured data sitting in neat columns.
Right.
Big data introduces a massive influx of unstructured and semi-structured data. When a company wants to analyze customer sentiment, they aren't just looking at star ratings. They are writing algorithms to parse the text of millions of raw tweets, analyze the audio tone in customer service phone calls, and process the visual data from security cameras in their retail stores.
Trying to run an analysis that combines a structured sales receipt with an unstructured audio file requires completely new types of analytical engines. The third V is velocity, and this is where the speed of modern business really shows.
Velocity dictates that data is streaming in and changing at an unprecedented speed. It is no longer acceptable to process data in massive nightly batches. Consider a global logistics company tracking a fleet of delivery trucks or a ride-sharing app like Uber.
Let's look at the mechanics of the Uber example. If I open the Uber app, my phone is pinging my exact GPS coordinates to their servers every single second. Thousands of drivers are doing the same thing.
That geolocation data has extreme velocity. If Uber's database only updated its supply and demand metrics once an hour, the surge pricing algorithm would be useless. It would be pricing rides based on where cars were 45 minutes ago.
Which doesn't help anyone.
Exactly. Big data architecture must ingest, index, and analyze this high-velocity stream in real time, allowing the surge pricing algorithm to react to micro-fluctuations in demand within milliseconds.
The infrastructure required to process data while it is in motion is incredible. And the final V is veracity.
Veracity addresses the messiness and trustworthiness of the data. Is the data meaningful, accurate, and free of anomalies? When you ingest millions of unstructured social media posts, the veracity is highly questionable. There are bots, sarcasm, typos, and false signals.
Yeah.
The business challenge of big data isn't just storing it. It is writing the filtering algorithms necessary to clean it. If an executive bases a $1 million strategic pivot on a high volume of data that lacks veracity, they will confidently steer the company off a cliff.
So, assuming an enterprise organization has successfully captured this massive volume, variety, and velocity of data and filtered it for veracity, where does it physically go and how is it used?
The filter data is channeled into business intelligence, or BI systems. BI systems function as decision support systems, or DSS. They aggregate the data to provide managers with a comprehensive dashboard illustrating historical performance, current operational status, and predictive future trends.
But the data itself must be structurally organized to be queried by those BI systems. It doesn't just sit in a massive pile.
The foundational storage architecture for business intelligence is the data warehouse. A data warehouse is a massive, multi-purpose repository that extracts data from various operational systems across the enterprise, transforms it into a standardized format, and loads it into a central database. Crucially, a data warehouse stores historical, non-volatile snapshots of data.
Non-volatile meaning it isn't constantly being overwritten by live transactions. It is a historical archive.
Exactly. Because it stores historical snapshots, managers can run complex comparative analyses like analyzing Q4 sales trends across 5 different geographic regions over the last 10 years.
Let's look at the architectural extraction process. If the data warehouse contains the entire historical breadth of the company's data, it must be massive and complex to navigate. If I am a mid-level manager in the human resources department, I don't care about the supply chain logistics in Asia, and I don't care about the marketing click-through rates. I strictly want to run analyses on employee retention, payroll, and benefits utilization. Do I have to write a query that searches through the entire global data warehouse to find my specific HR metrics?
You do not, because database architects build data marts to solve that exact problem. A data mart is a highly focused subsection of a data warehouse. It is designed strictly to serve the needs of a single business unit, department, or function.
Functionally, how does the architecture of a data mart differ from the main warehouse?
A data warehouse is normalized to store everything efficiently. A data mart often uses a denormalized structure like a star schema, where the data is pre-aggregated and optimized specifically for the types of queries that department frequently runs.
Oh, that makes sense.
This drastically reduces the computational power needed for the HR manager to generate their report and it insulates the main data warehouse from being bogged down by thousands of daily departmental queries.
The Tedmon and Wilhelm text outlines three specific architectural types of data marts that students need to recognize.
Yes. The first is a dependent data mart. This architecture extracts its data strictly top-down from the centralized data warehouse. It acts as a specialized lens, looking at the main repository.
In second.
The second is an independent data mart. This is built entirely separately from the data warehouse, often to serve a specific isolated function without the massive overhead of integrating with the enterprise system.
Though I imagine independent data marts can lead to data silos if a company isn't careful.
They absolutely can. Which leads to the third type, the hybrid data mart. A hybrid architecture pulls core organizational data from the central data warehouse, but it also has the capability to ingest and integrate external data from outside systems or third-party vendors.
Even with data marts optimizing the queries, running predictive analytics on terabytes of historical data must require immense computational horsepower. Historically, if I asked a database to cross-reference 5 years of sales data, I might hit enter and go get a cup of coffee while the hard drive spun up and searched for the answers. How do modern analytical platforms process this big data in real time?
The paradigm shift in processing speed comes from advanced hardware integration, specifically in-memory computing and massively parallel processing platforms. Historically, as you noted, the bottleneck in computing was disk latency. The CPU had to wait for physical magnetic hard drives to spin, locate the data, read it, and transfer it.
Disk I/O input-output operations were the slowest part of the chain.
In-memory computing eliminates that bottleneck. It uses sophisticated middleware to load massive terabyte-scale datasets directly into the system's random access memory distributed across a network of servers. RAM operates at lightning speed compared to physical disks. By keeping the active data entirely within the short-term memory layer, the CPU can execute complex analytical queries almost instantly.
And this is usually packaged into enterprise-grade hardware.
Yes, companies purchase dedicated analytic platforms, such as IBM's Integrated Analytics System. These platforms utilize massively parallel processing, or MPP.
What does that mean?
Instead of one powerful CPU trying to read the whole database, the platform divides the massive analytical task into thousands of smaller computational chunks and processes them all simultaneously across a massive network of integrated servers.
So we have the high-speed storage and we have the processing power. Let's talk about the analytical tools the managers actually use to dig into the data. The text highlights OLAP and data mining. They serve two fundamentally different analytical purposes. Let's start with OLAP.
OLA stands for Online Analytical Processing. It is a powerful software capability integrated into most BI systems that allows users to perform high-speed, multidimensional analysis. The key architectural difference is that OLA does not store data in two-dimensional tables. It stores data in structures called data cubes.
A data cube. Explain the mechanics of a multidimensional cube compared to a flat table.
A flat table gives you two dimensions, like looking at sales revenue by region. But a manager usually needs more depth. They want to see sales revenue by region, broken down by product category, broken down by fiscal quarter.
Okay.
An OLAP data cube physically pre-calculates the intersections of all these dimensions. It allows the manager to instantly slice and dice the data. You could rotate the cube to look at the data from a different intersecting angle without having to write a complex new SQL query.
So OLAP is the perfect tool for report creation, forecasting, and running specific what-if scenarios. But OLAP requires the manager to know exactly what question they want to ask. If I want to know the sales of blue phone cases in Texas during Q3, OLAP will instantly hand me the pre-calculated number. But what if I don't know what questions to ask? What if my business is failing and I don't know why?
That is the exact use case for data mining, also formerly known as knowledge discovery in data, or KDD. Data mining does not wait for a human to ask a question. It unleashes sophisticated mathematical algorithms and machine learning models upon the massive data stores to autonomously search for hidden patterns, anomalies, and correlations that a human manager would never logically think to look for.
The Tedmon and Wilhelm text provides a brilliant demographic example of this. Walk us through how an algorithm discovers hidden business value.
Imagine a large consumer goods corporation utilizes data mining on their customer database. The algorithm cross-references millions of data points and discovers a highly specific, hidden pattern. It reveals that female consumers earning between $75,000 and $100,000 annually who also subscribe to a specific subset of female-targeted magazines are statistically highly likely to purchase a completely unrelated, specific consumer product manufactured by the company.
A human marketing director would likely never sit in a boardroom and hypothesize a connection between a specific magazine subscription and the sale of an unrelated household product. There is no obvious logical link, but the algorithm simply ran the math and found the correlation.
The algorithm found the pattern. However, this raises an important question, because the business professional must exercise critical thinking here. Data mining comes with a profound warning. Data mining yields probabilities and statistical correlations. It does not prove exact causal relationships.
Let's emphasize that distinction: correlation versus causation.
If a business confuses the two, they will make disastrous strategic errors. The data mining algorithm proved that the magazine subscription and the product purchase frequently occur together. But you absolutely cannot assume that these women buy the product because they read the magazine or because they belong to that specific income bracket.
Right, there may be a hidden third variable driving both behaviors.
Exactly. The data mining tells you what is happening with mathematical certainty. It does not tell you why it is happening.
The insight gives you a target for your marketing spend, but you still need human intelligence to understand the psychological driver. Now, earlier we discussed the variety of big data, specifically unstructured web data. Do data mining algorithms work on the unstructured chaos of the internet?
They do, through a specialized discipline called web mining. Web mining applies data mining principles to extract actionable information from websites, e-commerce platforms, and the vast expanse of social media. The discipline is categorized into 3 distinct types: web content mining, web structure mining, and web usage mining.
Let's break those down. Web usage mining sounds like the oldest of the 3.
It is. Web usage mining, often referred to as log mining, involves analyzing the server access logs. It tracks exactly how human users navigate through a website. Where do they click? How long do they hover over a product? Where do they abandon their shopping cart?
So e-commerce companies use this data to optimize the user interface and streamline the checkout process.
Exactly.
Web structure mining, I imagine, is the foundation of search engines.
Correct. Web structure mining analyzes the underlying architecture of the web itself. It maps out the hyperlinks, evaluating how different pages and domains connect to each other. This is how algorithms determine the authority and relevance of a website, which directly dictates search engine rankings.
But web content mining is where the technology truly borders on science fiction. This is the extraction of meaning from the actual text, images, and videos posted online. Consider this scenario. A user posts a photo on social media. It is just a snapshot of their cat eating a piece of cantaloupe out of a bowl on the kitchen table. In the background, there is some messy kids' artwork hanging on the refrigerator. To a human scrolling by, it is just a funny, relatable cat picture.
But to a web content mining algorithm utilizing computer vision and natural language processing, that single image is a treasure trove of highly monetizable psychographic data.
Exactly. The algorithm scans the image and systematically tags the user's profile. It identifies the cat, instantly classifying the user as a pet owner and a target for premium pet food ads. It identifies the cantaloupe, flagging a potential interest in fresh foods or health-conscious eating.
And it spots the artwork on the fridge.
Right, confirming with high probability that the user is a parent of young children, opening them up to toy and educational marketing. It even analyzes the messy state of the kitchen, which might indicate a busy lifestyle, triggering ads for time-saving meal delivery services.
From one seemingly innocuous photo, the algorithm constructs a rich, multi-dimensional psychological and demographic profile that will heavily dictate the SEO optimization and targeted marketing that user experiences for the next fiscal quarter.
Which is incredibly powerful for the marketing department, but deeply unnerving from a privacy standpoint. I mean, when an organization has the technical capability to compile that level of intimate predictive data on millions of consumers and highly sensitive personal data on its own employees, the operational risks skyrocket. A database is no longer just a ledger, it is a massive liability.
Which is exactly why enterprise organizations must implement rigorous data governance frameworks. Data governance is the overarching strategic authority that manages the availability, usability, integrity, and security of the data employed in an enterprise. The core of this governance is the establishment of information policies.
Information policies are the strict, codified rules determining exactly how data is acquired, how long it is retained, how it is distributed, and most importantly, who has the authorization to view it.
Let's apply this to a university setting. A university's central database contains an immense variety of highly sensitive information. Your permanent home address, your financial aid details, your medical records from the campus clinic, and your academic transcripts.
Right.
The information policy, dictated by federal laws like FERPA explicitly mandates that only specific, authorized faculty and administrative staff have access to your educational records.
It relies on the security concept of least privilege. A financial aid officer can see your scholarship data, but they are physically locked out of your medical records. The campus doctor can see your medical history, that they cannot access your GPA. Who actually builds these digital walls and enforces these policies within the system?
The enforcement and architecture fall to the specialized database personnel. The text outlines 4 critical roles. The database administrator, or DBA, is the senior authority. The DBA is responsible for the overall maintenance, performance tuning, and ultimate security of the database. They install the software, allocate the physical storage, and grant the user permissions.
And working under the DBA.
You have the database developer. The developer is the architect who actually writes the SQL code, designs the ERD schemas, and builds the complex queries and automated reports that the business requests.
So the DBA manages the environment and the developer builds the structures within it.
Then you have the system administrator. Their focus is broader than just the data. They manage the physical hardware servers, maintain the operating systems, ensure network connectivity, and engineer the disaster recovery protocols. Finally, you have the data analyst or data scientist.
What do?
They don't build the database. They are the end users who extract the data, run the mining algorithms, and translate the mathematical output into actionable business intelligence for the executive team.
Let's focus on the DBA's most critical responsibility, database security. Data breaches are a constant headline, costing corporations millions in fines and lost reputation. If I'm a DBA, how do I actually protect this centralized repository of wealth?
A modern, robust security strategy relies on a zero-trust architecture. Historically, if a user logged in from a computer inside the corporate office building, the system trusted them. Zero trust assumes the network is always hostile.
Always hostile.
Yes. It dictates that no user or application is trusted by default, regardless of whether they are internal or external. Every single request to read or write data must be rigorously authenticated and authorized. DBAs implement this through 3 layers of database security.
Walk us through the mechanics of those 3 defensive layers.
The first is the perimeter layer. This represents the outer walls of the fortress. It involves infrastructure, security firewalls, virtual private networks, and secure email gateways. The perimeter layer's strict function is to block external unauthorized traffic from ever reaching the database servers.
But if a hacker steals an employee's password, they bypass the perimeter entirely.
Which is why the second layer is critical, the access layer. The access layer controls the internal users who have successfully bypassed the perimeter. It enforces the information policies we discussed. It relies on identity and access management protocols to ensure that even with a valid login, the marketing intern only has permission to read the marketing tables and is technically barred from executing a command to view the HR payroll files.
So the access layer contains the internal threat and the final defense.
The database layer itself. This involves the native software rules configured within the DBMS. It includes encrypting the data at rest on the hard drives, encrypting the data in transit across the network, and implementing strict input validation rules in the data dictionary to prevent malicious code like a SQL injection attack from executing within the engine.
But security isn't just about hackers, it's about system resilience. Servers experience hardware failures. Data centers lose power. What happens to the integrity of the data if a massive, complex transaction is executing and the power grid goes down halfway through? Does the database become permanently corrupted?
It does not, because relational databases utilize sophisticated recovery techniques based on the transaction log. A transaction is a sequence of operations treated as a single atomic logical unit of work. Before a DBMS makes a permanent change to the primary data tables on the hard drive, it first writes the intended change to a highly secure, sequential transaction log.
It maintains a strict journal of its intentions.
Exactly. This allows the system to execute 2 main recovery techniques: rollback and commit.
Let's explain rollback, also known as undo recovery.
Imagine a complex financial transaction is halfway through updating 50 different tables, and the server crashes. When the server reboots, the DBMS checks the transaction log and sees that the transaction started, but never logged a completion signal.
Okay.
Rollback recovery immediately steps in, reads the log backward, and systematically undoes every single partial change that was made to the tables. It returns the database to the exact mathematically consistent state it was in a millisecond before the transaction began.
It is the ultimate CTRL-Z. It ensures that a half-finished transaction doesn't leave the business logic in a corrupted, unbalanced state.
And commit recovery.
Commit recovery or redo handles the opposite scenario. The transaction fully finished, and the DBMS logged a commit signal confirming the data was valid. But before the data could be written from the temporary RAM down to the permanent physical hard disks, the system crashed.
The live tables are empty, but the transaction log has the complete verified record. Commit recovery reads the log forward and systematically reapplies all those changes to the permanent disks, ensuring the authorized data is restored.
So the data is secured against hackers, and the architecture is resilient against hardware failure. But I want to pivot to the ultimate operational question. We spent this entire deep dive discussing the brilliant mechanics of storing and retrieving data. What happens when the underlying data itself is just wrong?
When data quality degrades, the technical perfection of the database becomes irrelevant, and the company bleeds capital. Poor data quality or invalid data input causes a devastating ripple effect across the entire supply chain.
Let's look at a concrete operational example of how a simple human error destroys the bottom line. Imagine a warehouse employee is manually entering an inventory shipment of our smartphone cases. They intend to log 3,000 cases received. They make a simple typographic error and miss a single zero. They log 300 cases into the DBMS.
The immediate operational consequence is that the centralized system now believes the company is facing a critical inventory shortage.
Right.
The ERP system, trusting the data integrity of the database, automatically triggers a massive emergency reorder protocol to the overseas manufacturer to replenish the stock.
Wow.
The company instantly spends tens of thousands of dollars manufacturing, shipping, and storing smartphone cases they do not actually need.
And the cascade continues. The warehouse is now over capacity. Capital is tied up in dead inventory. And to make the scenario even worse, what if the product wasn't a plastic phone case? What if the company dealt in perishable goods like pharmaceuticals or fresh food?
The financial loss multiplies. The unnecessary inventory expires in the warehouse and must be written off as a total loss. A single missing zero on a keyboard directly results in a six-figure destruction of capital.
Wow.
And bad data affects customer-facing operations just as severely. If your DBMS is plagued by duplicate records, your marketing department is actively wasting budget by mailing two identical catalogs to the same household. Furthermore, it completely undermines the credibility of your sales force. When a salesperson calls a major client to renew a contract, but their CRM dashboard pulls an outdated, inconsistent record of the client's past grievances, the salesperson appears incompetent and the account is lost.
The cost of bad data is existential. So how do modern corporations fight back against human error and systemic data degradation?
They fight back using data quality audits and data scrubbing. A data quality audit is a comprehensive statistical evaluation of the database. Analysts assess the accuracy, completeness, and consistency of the source data. They don't just fix the errors, they map out where the errors are originating. Perhaps a specific web form is poorly designed and confusing customers, and they monitor the data pipelines over time to identify systemic bottlenecks.
The audit diagnoses the disease. Data scrubbing is the surgery.
Correct. Data scrubbing, or data cleansing, is the tactical implementation of specialized software tools that automatically scan the millions of records in the database. The software hunts down and merges duplicate records, utilizes algorithms to correct common misspellings, fixes syntax errors, and forces standardized formatting across the entire enterprise.
It acts as an automated digital janitor, constantly working in the background to sweep the tables and ensure the analytics engines are feeding on high-quality fuel. And as we look to the future of the industry, that digital janitor is becoming exponentially more intelligent. How is artificial intelligence structurally altering the landscape of database management?
AI is driving a paradigm shift in both accessibility and optimization. First, it is breaking down the technical barrier to entry. Historically, to extract insights from a relational database, you need to know exactly how to write complex SQL join statements. Today, AI integrations allow managers to use natural language processing.
Meaning you can interface with the machine just like you would a human analyst.
Exactly. A marketing director can simply type into the prompt, "Show me a bar chart comparing the sales trends of the midnight blue phone case in the Northeast region versus the Southwest region for the last 3 quarters." The AI dynamically translates that natural language into the necessary, complex SQL queries, executes the search against the DBMS, and generates the visual chart in seconds. It empowers every manager to act with the speed of a data scientist.
Furthermore, AI is solving the problem of variety in big data. AI models can structurally analyze an uploaded image of a handwritten invoice, extract the relevant text, categorize the purchase, and cleanly insert the structured data into the relational tables without human intervention.
Behind the scenes, AI is also optimizing the database resources. Machine learning algorithms monitor query patterns and automatically build or adjust indexes to ensure the CPU is operating at maximum efficiency, drastically reducing processing costs. And critically for the bottom line, the fusion of AI and big data is revolutionizing cybersecurity and fraud detection.
Because AI excels at pattern recognition on a scale humans cannot comprehend.
An AI algorithm monitoring a financial database can analyze millions of credit card transactions per second. It establishes a baseline of normal behavior for every single user. If an anomaly occurs, a transaction that deviates from the established pattern by a fraction of a percent, the AI can flag it and freeze the account in milliseconds, preventing the fraud before the transaction ever commits to the ledger.
It is truly staggering to step back and look at the evolutionary arc. We have moved from physical paper files stored in metal cabinets, vulnerable to a single spilled cup of coffee, to globally distributed, AI-driven architectures capable of analyzing human behavior in milliseconds and processing 20 million requests a second. The underlying engine of global business has never been more sophisticated or more critical to understand.
A business professional today does not necessarily need to know how to write the code to build the engine, but they must absolutely understand how the engine works, what fuel it requires, and what its limitations are.
That is the perfect summary and a great place to conclude our deep dive into Module 2 databases. A massive thank you to our listeners for joining us today, specifically our ambitious students and professionals from the Dr. Sam Pack College of Business at Tarleton State University.
It has been a privilege to unpack this architecture with you all.
Before you close the app, I want to remind you one more time to like, subscribe, follow, and share the deep dive. And we specifically want you to engage in the comments down below because we have a targeted discussion question for you to analyze.
Consider your own career trajectory or a specific business you frequent daily. If you were appointed as the primary data architect managing their database, what specific, non-obvious pieces of data would you prioritize tracking to gain a competitive edge? And conversely, how would a specific instance of bad data, quality like a corrupted foreign key or a redundant customer, record directly damage that company's operational bottom line? We want to read your specific strategic examples in the comments.
I'll be reading through those comments this week. And I want to leave you with a final, somewhat provocative thought to mull over. We talked extensively today about web content mining and algorithms building psychographic profiles from simple photos. As AI becomes deeply integrated into these massive data warehouses, we are rapidly approaching a threshold where a corporation's database might definitively know that you are pregnant, or developing an illness, or preparing to quit your job before you have even consciously realized it yourself. When the predictive algorithms stored in these databases know us better than we know ourselves, who ultimately owns the rights to that digital reflection? It is a question every future business leader will have to answer. Next time on the deep dive, we are shifting from the architecture of storing the data to the strategy of weaponizing it. Get ready for Module 3, Data Analytics, where we will explore exactly how organizations transform these massive, inert data sets into undeniable, actionable, competitive advantages. Until then, the next time you order something seamlessly on your phone, take a moment to appreciate the complex, invisible engine making it all happen. Thanks for listening.